Welcome everybody to the last webinar of the Neuroergonomics series today. It's on social neuroergonomics, and I'm excited to first introduce you to the field of neuroergonomics and the editorial board, and then also present you with a short overview over the 5 grand challenges that we as an editorial board have identified for the next, at least 10, 15 years for us to work on. And then I'm even more excited that we could convince an amazing set of keynote speakers to share with us their pioneering research in that field. So very excited about this webinar. So let me first introduce you the board of the social neuroergonomics branch within Frontiers in Neuroergonomics. On the one hand, that's Frank Krueger. He's the specialty chief editor. He unfortunately couldn't make it today because of a family emergency, but he is the specialty chief editor. He's currently a professor of social neuroscience at George Mason University. His research interests include the neural underpinnings of social beliefs, neural correlates of trust in social diets, and neural signatures of social norm violations. And then on the other hand, it's me. I'm the assistant specialty chief editor. My name is Eva Wiese. I'm currently professor of cognitive psychology and cognitive ergonomics at the Berlin Institute of Technology. And before that, I've been a professor at George Mason University as well for about 8 years. My research interests include causes and effects of mind perception in human-robot interaction, social cognition in dynamic human-robot interactions, and cognitive offloading and embodied cognition with a focus on offloading cognitive processes to social agents, such as social robots. We have an amazing editorial board. We have a lot of research editors too that I couldn't list on these slides, but you see here our associate editors. We are always interested in having more associate editors. So if anybody feels called, please contact us and join our editorial board. Together as editors, we cover a very broad area of expertise within the field of social neuroscience and human factors. And that includes mental states classification, brain-computer interfaces in social interactions, social robotics, trust in automation, biometrics, artificial intelligence, human factors in transportation and medical systems, adaptive social technologies, hyperscanning, mobile neuroimaging, human-machine teaming, telepresence, rehabilitation, and many, many others. Before I talk about the challenges that we as an editorial board have identified in the field of neuroergonomics, let me briefly define what we mean when we say social neuroergonomics. First, and people who have attended other webinars of the series have seen this definition before, neuroergonomics is defined as the study of the brain at work in everyday life. That's a definition by Raja Parasuraman in 2003. So neuroergonomics as a field aims at understanding human brain function, underlying human interaction with technical systems. Social in this context, and this is not a definition that's complete, but it gets us quite, it defines social machines quite well. Social refers in this context to machines that are autonomous, that are physically embodied, that interact with other physical agents by following social norms and behaviors that are associated with their role, display physical and or behavioral signs of human likeness. So that means they look like humans, or they have certain features of humans, or they behave like human agents do. And that's most important here, trigger behavioral and or neural patterns reminiscent of human-human interactions. Social neuroergonomics as a field is a transdisciplinary field devoted to the application of knowledge of the neurobiological underpinnings of social processes and behaviors to the design, engineering, and evaluation of human-machine systems. So that means that we are really interested in the entire range of neurobiology, neurophysiology, neuroscience, ranging from single cell recordings or even molecular and genetic processes to looking at behavior and neuroimaging studies with human participants. And then design, engineering, and evaluation means that we are interested in studies that deal with developing or the conceptualization of social machine systems, the actual implementation or the engineering part of those systems, and then also the neuropsychological or psychological evaluation of these systems. And for neuroergonomics as a field, we really want to have this balance between, or like this combination of understanding the social nature of human brains. So like that would be the basic research part, and the principles of human-centered design. So that would be more the human factors and engineering and computer science part. And by combining these two areas, social neuroergonomics has the potential to advance our understanding of the psychoneurobiological basis of human social interactions with technology, and to use these insights to foster more efficient and also satisfying human-machine interactions. So after this very brief introduction and broad definition of the field, I'd like to introduce you to the challenges in neuroergonomics, social neuroergonomics, and we need to make a minor adjustment to our neuroergonomics icon for this, but now we are ready to dive right in. So Frank, Krueger, and I have written up these grand challenges in a short article that you can check out if you like in Frontiers in Neuroergonomics. And we have said that the first challenge is really to move studies in this field from observation to interaction. And what do we mean by that? I'm sure you all know that in the past, and my research is certainly guilty of that as well, we have used very static, non-dynamic paradigms where people just watch certain stimuli that are presented in a very predictive manner on the screen while lying in a scanner or sitting in an EEG cabin doing an experiment. Social neuroscience has provided evidence for quite some time now that that is okay as an approach, but it doesn't accurately depict or summarize all of the really core social processes that are going on in dynamic social interactions between social agents. So what we really need is a so-called second person framework where you examine neural mechanisms in real time, reciprocal social interactions between humans and machines. So here's an example. On the left would be an observation paradigm where people look at a classical paradigm. In this case, it's one of my studies, a gaze cueing study with a social robot while lying in a traditional fMRI scanner. On the right side, this is a paradigm that my colleague and friend Agnieszka Wikowska has used in her lab at IIT in Genoa. It's an adaptation of the gaze cueing paradigm now using EEG with a real social robot in a relatively realistic environment, allowing dynamic interactions between the human and the robot. And social neuroergonomics as a field should really help develop, test, and validate such new dynamic paradigms, and not only focus on short-term or one-time interactions between humans and machines, but also look at how these interactions and these patterns of social cognition develop over time. And ideally in everyday environments, and potentially even, and I know it sounds challenging, but hey, these are the challenges of social neuroergonomics, with easy to use off-the-shelf products so that we can reach a wide range of customers that potentially have accessibility issues or maybe even cognitive impairments, so that it's not just research that happens in the lab, but also is available to real people in real life. And so I'm sure most of you know that little Cosmo robot. It's just one example. There are many, many more, but it's a very affordable robot where the company gives you access to the SDK, so you can program the robot and there's even shared code on GitHub. So it's also open science community here where, people really share their codes, and it is really nice to do research with this platform. And we have done studies, for instance, where we asked people to take Cosmo home and interacted with Cosmo at home, and then asked people to come back to the lab. And then we did an EEG study where we looked at reward processing, where they gambled for Cosmo or for another human. And we could show that certain EEG components that are related to reward processing are impacted by how familiar people were with that robot, and found some systematic relationship between the duration of the interaction and how rewarded people felt when they gambled and won for Cosmo, for instance. The second challenge is really from automation to autonomy. And here, the challenge is that social neuroergonomics needs to foster a shift from automated, that means predefined and rule-based systems that still work in structured environments, to fully autonomous systems. For instance, adaptive artificial intelligence systems that can operate and adapt in changing environments. And that one of the challenges here, and that's not the only one, but one of the challenges, since we're talking about social neuroergonomics, is how do, for instance, people perceive robots or other social embodied agents as having a mind of their own? So being able to act and plan and experience the world around them. One example here also, again, from our research, we have, for instance, used a video game called Don't Starve Together, where people play online, and where you can have one character being played by the participant and then another player either being played by another human or by an artificially intelligent system. And we have played around here with different socially artificial systems, and first did a Turing test where we wanted to see, can people actually distinguish if they are playing against a human or if they are playing against an AI? And then also, depending on what they believe who they are interacting with, does that have an impact on pro-social behavior or on punishment? So you can, for instance, here team up with other characters and fight together against others, or you can share goods, or you can, give another person a gift. And it's still very, early, and I can't really share a lot of data yet because we are still piloting. But it is really interesting how strongly social behaviors in this relatively complex dynamic environment are impacted by beliefs about the social nature or the human nature of the interaction partner. And in general, at some point, all of these research efforts should really help us to formulate minimal set of design features that really help trigger those very social areas in the human brain in a way that is similar to what we see in human-human interactions. The third challenge is from explicit to implicit measures. That is one of my favorite topics, because I'm sure we have all been there where we saw research that seemed fantastic, great human-robot interaction, and you have this high expectation that now you get this major insight, and then most of the dependent variables are subjective ratings. Again, I'm not judging anybody. I have done that myself. I'm still doing that. So it's not to say we can't do that anymore. The message is more, try to think about also incorporating other more implicit measures. So the challenge really is to at least combine explicit, so controlled, slow, conscious process measures, and implicit measures that measure more automatic, fast, and subconscious processes. And to, in general, create insight or generate insight about how these explicit and implicit processes work together in dynamic human-machine interactions. So, and I want to give you another example from my own research. Here we were wondering which robot or agent people which robot would be best to perform a certain task with. And we used a morphing procedure where we morphed a human face into a robot face. And what you see here is essentially faces that vary in human likeness from 0% to 100%. And so what we actually did first was really use explicit measures where we asked people using a 7-point Likert scale, do you think this agent has a mind? Do you think this agent would feel pain if it fell? Do you think this agent is likable? And so on and so forth. And what you usually get when you do this is when you manipulate physical human likeness, you get a somewhat linear pattern, or at least, monotonous pattern, where as you increase physical human likeness, ratings usually go up. Then we embedded the same images into a behavioral task, in this case, a vigilance task, where we measured sustained attention. In this task, you see one of the agents first look at you, then change gaze direction, and then either look at or away from a gun or a hairdryer. And it's a sustained attention task, and participants only have to press a button when the agent looks at a gun. It doesn't matter if it's a human-like agent or a robot-like agent, you only press when this event happens. And because it's a vigilance task, this event doesn't happen very often. So over time, your hit rates go down, your false alarm rates go up, and your reaction time goes up as well. That's called the vigilance decrement. And so I'm showing you now the results of this study. And you see that the pattern looks very different. The more negative the bars are, the stronger, the bigger the vigilance decrement. That means the worse, the more impacted the sustained attention performance was over time. And what you really see was interesting is that the 70% human agent, so what's always described as maybe the uncanny agent, creates or causes the strongest vigilance decrement. And when you compare the pattern on the left and the pattern on the right, you see that your data on the left is not very predictive of the data on the right. So this is just one of very many examples that really motivated me to think more consciously about combining these explicit and implicit measures and put effort into using more implicit measures in the future. And that is still obviously not very dynamic here. This is still research that's done on a computer screen. So in the future, this should be combined with the challenges that I mentioned before, where we want to use implicit measures also in a dynamic social interaction in real life, ideally. And this is another example here where we have actually started to use now in an entrainment task. So we're now taps with another human, and where we wanted to see if synchronization in tapping frequency is somewhat correlated to your prior exposure to now, and also still ongoing research, but we see some evidence there that the more familiar you are with the robot, the more quickly you synchronize your tapping frequencies with the robot, and the more you stay in sync if you don't get visual feedback anymore from the robot's tapping. So just as examples, I'm very excited to see some of the keynote speakers' examples later. It's just for illustration purposes here. Challenge number 4, from diets to groups. So here, we know that most social neuroscience or even human-robot interaction research was mainly focused on interactions between one human and one robot or one machine. But we need to expand this, obviously, to interactions between humans and machines in groups and mixed groups and even cultures. Because when you only look at diets, they lack certain group-specific manifestations that social agents and social agents are often asked to assist and interact with groups of people. So we must understand these processes in human-robot group interactions. We have done here, for instance, a task on the ASH paradigm, where We looked at the influence of a consistently but incorrectly answering majority of computers, robots, and humans on conformity in human participants. We have slightly modified the task. I don't need to go into detail here, but essentially we have we had a social task where people have to make a judgment about emotional states, and an analytical task where people had to do an arithmetic task. And before they gave their answer, a certain number of computers, robots, or humans have given an answer. And what we find is that depending on task, you see a strong impact of agent type, where if you do the social task, the computer and the robot have a significantly less strong impact on conformity than the humans. And again, these things, this is just an example. We need to expand that kind of research to more diverse cultural populations and need to focus on human-machine teaming in the future. Which brings me to my the last challenge, from lab to natural environments. What we all want to do, but what is often very difficult once we start doing it. We all know that in particular, neuroscience measures are often very invasive and restrictive and do not easily allow for dynamic social interactions, in particular if you have a machine in the picture. And the challenge here is to really start in the lab and use the insights that we gain there on regions of interest, and really use mobile neuroimaging tools. And I hope some of the keynote speakers will show us how they solve this problem for now, and combine it with easy to use social robots and computational analysis methods to really see how, if the same brain areas are also activated in complex dynamic environments. And we really need these interactive paradigms that start in the lab and then transfer to the wild. And again, I've mentioned that earlier, these off-the-shelf robots like Cosmo, for instance, because they are so cheap and easy to use, you can easily use them and give them to participants so that they can take them home and that they can really interact with them for a long period of time, and then come back to the lab and then do traditional social neuroscience experiments in the lab. Or also another interesting thing, George Mason has these Starship robots on campus now, and there are more and more of these environments now where you really have robots interact with people in complex environments. So that's obviously another interesting set where we can do these realistic studies in the wild. That brings me now to introducing our fabulous keynote speakers, who one after the other will address one of the 5 challenges that I've just introduced. And because those are very distinguished people, we need to make a modification again. We will start with Emily Cross. Emily Cross is currently a professor of social robotics at 2 universities, University of Glasgow and Macquarie University in Australia. Emily's research focuses on social robotics, but also action perception coupling and perception of aesthetics. And she will talk about challenge 1, or she will address challenge 1. And her talk is, the title of her talk is Probing the Flexibility of Social Perception Reveals Important Insights into Observation and Interaction. Then we will move on to Peter Hancock, who is Pegasus Professor, Provost, Distinguished Research Professor, and Trustee Chair at the University of Central Florida. Peter will address challenge 2, from automation to autonomy. And the title of his talk is Malicious Intent, the Crumbling Boundaries of Individual Humanity. Then we will move on to Lorna Quant. Lorna is Assistant Professor of Educational Neuroscience at Gallaudet University. Her research focuses on using behavioral and neural tools to understand sign language, and she uses virtual reality and social robots to help with that. And the title of her talk is Embodied Sign Language Learning in Virtual Reality, Using EEG as an Implicit Measure of Learning. Then we will move on to Brian Saselati, Professor of Computer Science, Mechanical Engineering, and Materials Science at Yale University. Brian is definitely a pioneer in social robotics. Every time I want to know if somebody has done a study already, I go to your website and check it out. And Brian will address Challenge 4, from diets to groups. And the title of his talk will be What Robots Teach Us About Human Behavior. And then last but not least, Antonia Hamilton. She is a professor of social neuroscience at University College London. Her research focuses on social interactions in healthy individuals, and she examines whether certain social cognitive processes develop in the same way in individuals with autism spectrum disorder, or if they develop differently. And she will address Challenge 5, from laboratory to natural environments, and that is also the title of her talk. I am very excited to your talks, and I hand it over to you now. So Emily, you can start whenever you're ready.
Yes, sorry, I'm just doing a little screen share action here. Oh, it says I can't share while you're sharing. Let's try again. Sorry, it's okay. Now then, can you see everything? Oh, not quite. It's this different shaped. Okay. Can the whole screen appear now? Everything look good? Perfect, wonderful, thank you. Excellent. Okay, well, tremendous, huge thanks, Eva, for that wonderful introduction to this entire webinar and to this entire field. I've already learned so much, and it's always lovely to see a whistle-stop tour of some of the most exciting research that's coming out of your lab at the moment. And just being part of today's session is really, really exciting. And I cannot wait to hear from our other speakers and to tell everyone today a little bit more about this first challenge. So we're going to be talking about from observation to interaction. And I'm going to tell you a little bit about some of the work that my team has done into probing the flexibility of social perception in order to reveal insights into observation and interaction, particularly with artificial agents. All right, so I'll begin by placing this research within a broader context. So this first challenge speaks about from observation to interaction. And if you think about it, observation and interaction of other humans is something that we're all doing continuously, pretty much from the time we wake up in the morning until we go to sleep at night. We are seeing, watching, and interacting with other individuals. And this is essential that we're able to do this and to read others' social intent and organize our actions with others in order to achieve all manner of trivial to really complex goals. So whether that's raising your hand in class, when we used to have in-class and in-person meetings to ask a question, or something as complex as climbing a mountain, running a race, or any of the other brilliant things we're going to be seeing in the Olympics over these coming days, all of these things require really quite sophisticated dance between perception and interaction with other people. So that's all well and good. The human brain has evolved over millennia to achieve this somewhat effortlessly and very quickly and efficiently. But an interesting question for many of us gathered here today and interested in what the future holds is, how is this neural and cognitive machinery that's evolved for observing and interacting and making sense of other people, how is this going to be co-opted, and how are things going to be different? What opportunities, what challenges might we encounter the more and more it's not just other humans that we're engaging with in our social spheres, but it's also really sophisticated and quite unusual artificial agents. So this is a really, I think, important question, and understanding how we can best understanding how people might coordinate, cooperate, engage with types of social machines that we see here and that we'll see across today. It's going to be really, really important. So we know that, as Eva has said, and you can't really pick up a newspaper or click on the news without hearing about, the rise of the robots, and there's more and more money being invested into artificial intelligence, into these artificially intelligent social machines. So there's a proliferation of these agents, but we still don't have quite a grip yet on what's going on in the human brain when we interact with them. There's this idea so far that, okay, well, if we see a robot playing basketball, we're going to pretty much, again, use the same kind of neurocognitive architecture that we'd use to make sense of a human. And we'll just kind of say that that's more or less the case, and we can use that as a template. But what my team and several others around the world are arguing is that, well, actually, it's not just when we see a robot doing something that's vaguely human-like, our brain isn't necessarily just thinking, oh, that's like a human in a robot suit, and I'm going to respond to it accordingly. There's actually a whole bunch of other things that are going on across the cognitive spectrum. It's not just social processes either. And we talk about some of these things in a recent paper, a colleague of mine and I, and we talk about the impact of Hollywood films, which is actually really quite peculiar, or maybe not just Hollywood films, but just media in general, how this is shaping our perceptions and interactions. As well as our understanding of tools and machines versus other non-human social agents in general. And kind of this important point that Eva mentioned as well, how much time you spend interacting with an agent. All of these things and many more besides are really going to shape how we're perceiving and interacting with artificial agents. So it's not just going to be that we can take human social cognition and kind of patch that on as a one size fits all. So I think this is an interesting space, and I think a lot of the talks that we're going to hear in this session today are going to help us understand some of that subtlety and complexity a little bit more as well. But we might want to be asking questions, or people in this group in particular, about how we perceive and interact with these artificially intelligent machines, but kind of taking this question back one more step and saying, well, why should we actually care about this if I'm not really interested in social neuroscience or social perception? Why is this interesting to me? And what I would argue kind of is a slightly bigger picture reason why we should care is that if we can understand the human neuroscience that kind of underpins these day-to-day or these even laboratory interactions with artificial agents, this should help us develop improved design and programming of agents that are more socially engaging and more socially cooperative with people. So ultimately help us to build better robots, which is important. And equally important, especially for those like me who are coming from cognition and brain science to begin with, is that a deeper understanding of the flexibility and limits of human neurocognition when we engage with humans or with artificial agents will help us to understand kind of fundamental truths about the human brain and human cognition and how we can learn and develop and flexibly adapt based on what our environment gives us. So I think there's some pretty big reasons why this is quite important stuff. So we have been examining questions in this domain for the past several years from a social neuroscience perspective. And we've been, I'm going to focus on some, I'm going to say slightly older work from our team, but we'll say more foundational work. And that's only because of the challenge that Eva has tasked me with. This kind of observation to interaction really kind of speaks to some of the earlier work we've done. But it kind of even the recent work as well is all variations on this theme. Of how we can use social neuroscience tools to better understand observation and interaction with social machines. So one of the kind of theories that we've borrowed from developmental psychology poses the question, to what extent are we kind of driven towards making sense of artificial agents based on this like me idea? So am I really seeking out self-other equivalences in the environment? And if that robot is dressed like me, or it talks like me, or it has kind of a movement pattern like me, is it going to be much more easy for me to interact with it compared to if it looks like something like WALL-E or any of the robots we see at that, or some of those interesting robots in the dark path that Eva just showed in one of her first slides? To what extent do these things matter? So one of the ways we've been getting at looking at these questions is to ask some questions about stimulus cues. So what does a robot look like in terms of how like me is it? Is it there in the room with me? Does it have a human-like form? Does it move in this really rigid way, or does it move in a human-like way? Also, what do I bring to the interaction? What's my prior experience with robots? Is this something that something that I'm really familiar with? I've watched a lot of films, or I've come into the lab to do lots of different experiments, or is this totally brand new and really exciting? What have I been told about this robot? What do I believe? What's my propensity to anthropomorphize? So all the things that I, as the human, bring to the table are really important and also quite difficult to pin down. And of course, the interaction between stimulus cues and knowledge cues is really important as well for understanding what's going to go on and how we're going to design agents that are optimal for whatever social task they're supposed to perform with people. So I'll give you a whistle-stop tour of 3 different studies where we've kind of addressed some of these questions. And I've just realized that I can't quite see my timing. I'll just use it on my phone. But Eva, I can see you. So you can, if you can give me a T when it's time to wrap it up, that would be great. One of the first questions we'll address here is how the neural mechanisms are impacted in social perception. Neural mechanisms that we know are engaged in social perception are engaged or not when we're observing non-human form and motion cues. So these are kind of the stimulus cues. Also, we'll address how visual cues and expectations about an agent's social origins shape our perception. And finally, we'll take one tiny step towards interaction. I know we're going to be hearing some talks a little bit later today, far more deeply interactive studies. And this one will just be kind of the tip of the iceberg about taking us from observation to interaction. So in this first study, we are interested in exploring how stimulus features shape perception of artificial agents. And we often make use in the lab of 2x2 factorial designs because they're particularly robust for the types of neuroimaging questions that we're interested in. So in this particular study, we had kind of 2 factors looking at the motion profile of agents. So we could have either kind of familiar human-like motion or rigid, jerky robotic motion. So you can already see that one of those motion types is like me, the other type, not so much. And then we can also add on top of that either a like me form, so a human form, or a very much unlike me form, a robot form. And what we did is we filmed a bunch of videos that would kind of fit the bill across this 2x2 factorial design. And we had a human breakdancer performing kind of natural movement and then more rigid robotic movement. And then we used stop motion cinematography to animate just a very cheap Lego robot to do those same movements as closely as possible. And what we found, this was across 2 independent fMRI experiments with 2 different participant samples, is that by and large, when people were watching the kind of more like me movement compared to the less like me movement, so the natural dance compared to the robot dance, we don't really see widespread engagement of these typical social cognition brain areas. Instead, we only see really early visual cortex coming more online for the more familiar social stimulus, whereas when people are watching the much more unfamiliar, unlike me, robot movement compared to the familiar movement profile, here we see quite widespread and robust engagement of parts of what we call the action observation network, but also parts of the brain implicated in more social processes such as perspective taking. So we have, it's tiny on the figure here, but we have bilateral premotor cortex and inferior parietal lobule, as well as occipitotemporal cortices. Interestingly as well, we ran this not identical study, but with the same stimuli, we ran this study with functional near-infrared spectroscopy with 4-month-old infants. And we find some really interesting corresponding evidence that suggests even very early in development, when infants have very little experience with the world, we're seeing similar patterns of findings using FNIRS in the infant brain. So what we can conclude from this is that stimulus cues to humanness in terms of form and motion weren't necessarily necessary for engaging brain regions associated with human action observation. And this is already kind of like the first chink in the armor to suggest that when we're engaging and seeing robots, there's a lot more flexibility in social information processing going on than what, lots and lots of social cognition work with humans might suggest in terms of how special humans are. So in our next theme, we're going to add another layer to the social perception question, not just ask something about what stimulus cues and what an agent looks like, but also what do you as an observer believe about that agent? So when we talk about stimulus cues and knowledge cues, this is hopefully a pretty clear example, and hopefully some folks will be familiar with the Austin Power movies, which I'm sure are very dated now. But the basic idea is for stimulus cues, that robot in that picture there looks like a robot. But for knowledge cues, the robots that are surrounding the protagonist, Austin Powers, in the film, they just look like normal humans. But if you know what to expect, they're actually robots that hide deadly weapons in strategic places. So once you know that about them, you can't see them in the same way. So another 2x2 factorial design here, kind of playing off stimulus cues, so a human form or robot form, as well as knowledge cues. And this is where we're telling people that what they're about to see either has human origins, kind of made from really intensive motion capture procedures, versus computer origins. So we can show people videos and say that these have been made with kind of hands-off computer algorithms. In reality, everything has the same origins, but we use a very elaborate manipulation to kind of cover story to tell people more about how these videos were made. And in the paper, we have lots of details to kind of go into that in more detail. But essentially, people are seeing quite simple videos like you see there, and hopefully those are playing. And as you can see, there's no difference between the kinematics or really for anything going on there, but we're just telling people that they're about to see different things. And just to kind of whip through what we've seen here, we're seeing that there's actually a much bigger impact of stimulus cues to non-humanness in terms of engaging kind of not just early visual regions, but extending kind of anterior along the fusiform gyrus in the human brain. And in terms of our belief manipulation, when we tell people that they're about to watch videos that have human origins compared to videos that have kind of more computer algorithmic origins, here we see these are slightly more subtle effects, but that there's parts of the brain implicated with kind of more perspective taking and social cognition, such as precuneus and the SPL that are more engaged when you believe you're seeing something with human origins. So in this final little piece, I'll tell you about, make sure that we're okay. Okay, I know we're running out of time here shortly. We just took the same sort of manipulation that I just told you about, and we also now asked about, okay, if people aren't just watching these videos on the screen, as Eva very aptly put at the beginning, that's not what the real world's like. So we've taken one tiny step closer to the real world and into social interaction by using a very minimal automatic imitation paradigm, which essentially is just looking at the extent to which another agent's actions influence your own actions. Because we know that automatic imitation is kind of a real foundational building block of human social cognition and perception. I won't get into this in too much depth here, other than to say that across another neuroimaging experiment with kind of this much more interactive paradigm, we kind of see that there's some evidence that suggests that our actions behaviorally are showing kind of different patterns than what the brain is showing in terms of how our beliefs and stimulus cues to animacy are shaping perception and interaction. So again, there's more of that in the paper, but we'll just leave it at that for there. So what I can say to summarize here is that what these kind of preliminary studies have shown is that sensory motor nodes of the social brain, or the action observation network, seem to respond to both human and robot cues in terms of motion especially. And there's nothing really special about humans per se when we're thinking about these brain regions, whereas the temporoparietal junction, and I did go through this result quite quickly in the last slide, but it's one part of the kind of social brain network specifically really seems to be more robustly tuned to humanness and does care whether something has human origins versus kind of simply is mechanical or comes from a machine or a computer algorithm. So that was some older work. I'm not going to go into this. This is just kind of a whistle-stop tour of some of the more recent work that my team is doing, where we're trying to maybe take a few steps towards these challenges that Eva outlined in her opening and in her opening slides, and that we're going to hear more about from other speakers. It's a complex space, but it's a very exciting space to be working in and to be trying to take up these challenges and to make some progress. And I'll just finish off with two quotes, which I think place this work again in a context that for why we should be interested in it and why many of us care about it. This technology writer, Eric Sofke, said that we're only barely scratching the surface of the brain's social algorithms, which become even more complicated and unpredictable when we interface with technology. This was said some years ago now. I think it's about 15 years ago, but that sentiment can't be more apt today. It is so true and so important. And then the health psychologist and social roboticist Elizabeth Broadbent also suggested in a recent paper that the further we go down the path towards making and interacting with artificial humans, the more truths we learn about ourselves. So again, coming back to this bidirectional benefit of kind of social neuroscience and social cognition feeding into social robotics and what we can benefit, we can each benefit with each other. I'd like to thank my fabulous team and funders, and thank you for your attention. And I look forward to the discussion later, and I shall stop sharing.
Thank you very much, Emily. Very inspiring. I'm sure there will be a lot of questions on this later. We need to move on. Peter, are you ready?
I am indeed.
Very good.
So my first job this morning is to turn on the timer, a piece of automation, perhaps the piece of automation, so that I don't run over time, and to thank the organizers for inviting me. I'm very much appreciative of their kindness. And my mandate today is to talk about automation to autonomy, but I have to put this within a much larger frame, because I believe that neuroergonomics, and especially the social aspect of neuroergonomics, it can and should play an essential role in our efforts to battle what are existential problems for the species. I've never believed that human beings will fade away, but I do believe that our civilization is certainly at risk at the present time. And so I will try to make my comments very relevant to those particular issues. So let me begin then with not even the 10,000 foot picture. Maybe we'll call it the Jeff Bezos height of 69 miles to begin with. Human beings took about 5 to 7 to 10,000 years to extract themselves from the belief that they are the center of the universe. It was a slow and rather tragic process, but eventually it was done, and we now understand that we are certainly not the center of the universe around us. However, that was in space, and I'm going to refer later to the problem of how we still believe that we are the center of the universe in time. And so at the end of my talk, I will be talking about something that I've been working on, particularly called temporal dissonance between humans and machines, and the intrinsic belief that human beings still retain that the real time is their time and their time scale, as the 15 minutes I just put on here today. So that's one particular position, but let's talk a bit about the existential problems, because automation to autonomy, I believe, holds the potential solution, or at least a line of possible solutions, in the same way that Benedict Cumberbatch was fighting away with Thanos, 1 in 10 million possible opportunities. So in this respect, what we find is that we've known for a long time that you cannot continue to use up the resources of a closed system, essentially a closed system, infinitely. And now we're beginning to see this expressed here rather more vehemently. Indeed, someone noticed this morning on our informal chat that the temperature in Seattle is much higher than the temperature in Orlando. And so these are implications and diagnostics that the planet on which we live is really facing a change that we cannot ignore. And as scientists, we should not ignore, because it becomes not merely our scientific obligation, but our moral obligation to use our skills and our abilities and our capacities to help answer and resolve some of those questions. And why should that matter to people in neuroergonomics? Well, I believe it should matter because I'm going to offer neuroergonomics as a potential solution. So to look back quickly, the famous Club of Rome report of 1970 suggested that one of the ways in which we constantly get ourselves out of the bind that Thomas Malthus pointed out is that we just keep inventing new technology. Don't worry about the energy problem, we'll invent some solar stuff. Don't worry about the fossil fuels, we'll invent some wind stuff. Now, human beings are pretty adaptive sort of systems, and we've tried to do that. And we're doing it and succeeding to greater or lesser degrees. But if you look carefully at the symptomatology that the Earth, the planet, is giving us, we're not doing it fast enough. And why might this be? Why might we look into the question of why it could be? And I believe the answer is found in the brain, in the human brain. So in general, human brains seek to optimize the local world around them. They don't always optimize, as Sir Herbert Simon told us, they quite often satisfies. They do well enough to do well enough. But systems in general seek optimization in a sort of predator-prey way. I'm sure if you ever go to Starbucks, you'll find that baristas don't optimize. They tend to satisfy us and give you a coffee. But in general, let's take that as a principle. So in a closed system, Local optimization, that is, the local optimization of any one group, will necessarily, in a closed system, lead to global dysfunctionality. And this is what we see now in cultures, in nation states, in various industrial, commercial complexities, where each of them are not necessarily nasty, evil, horrible people, as are represented in Hollywood and some of the more lurid magazines and information sources we have. They're merely trying to do the very best they can with the rules of the game around them. But what I've put together in some work, the humanity of humanless systems, is that this is necessarily a battle that will take place. And so how can we resolve that battle? How can we accept that everyone, for example, listening to this, I see Lorna there trying to do her very best in the world, and Lorna is obviously trying to optimize. Eva is doing great work in her local area. How can we take those and say the world is now not a zero-sum game? How can we take those individuals and their aspirations and now combine them? And so what we have to do is we have to look at the regulation of human behavior in relation to a technical context. I'm not going to argue with the Club of Rome that technology is a critical factor in survivability, but it's the way in which human beings interact with that critical technology that is most important. And so when Eva and her colleagues asked me, I considered two things. What are the dangers if neuroergonomics succeeds, and what indeed are the risks if neuroergonomics fails? And so that's the general framework about which I'm now approaching automation and autonomy. So first of all, let's again delve into history. As I've said before, and I think it bears repeating, if you want to see well into the future, you have to see clearly into the past. Automation is not new in human societies. It's been around probably as long as human beings have created some sort of tools. It's just that some forms of automation don't look particularly sexy, shall we say. I'm reminded of a wonderful gutter system in the Sikh in Petra, which was there to channel water down to the area of the treasury and beyond from reservoirs that were collected. It's an automatic system. It's not particularly dynamic, but it does its job very well. And this is some even thousands of years old, as we can point to others that we see in the history. And I personally, of course, always like Emperor Rudolph II and his collection of automata. So the first thing is that automation has been around almost as long as human beings have. But now we're into this cusp change where we're talking about autonomy. And so in some senses, that system in the Sikh, for example, the canyon that you see on Indiana Jones, is autonomous. It doesn't require someone to do anything other than maintain it. But when it's working on its own accord. And so what I've come to believe over the past 2 or 3 years is that one of the problems lies in nomenclature. I wrote some work with Robert Hoffman on words matter, and I believe words matter. So what we mean by autonomy is often, as the previous speaker said, we tend to couch the concepts in terms of our own human approaches to it. And I've come to begin to change my mind on the presence of autonomous systems more recently. So let me try and explain that. If we don't couch autonomy as a human representation of autonomy, that is a sort of personally embodied freedom to navigate around, think our individual thoughts. If we actually begin to think of it as self-directed behavior at any level, then autonomous systems are not a thing for the future. They are a thing of the present and are growing. And in particular, I'm beginning to believe that large-scale social media systems try to begin to optimize for their own local world. They're not necessarily intentive in human intent, other than a very global sort of idea of returning profit on the investment in there. So I think what we begin to see is that autonomy is around us. It's already being embraced. And so when I generated an Isles of Autonomy metaphor for its growth, I begin to see the Isles beginning to rise more above the ocean of human action, much more than I thought I would even 5 years ago. So what's this to do with, in this case, neuroergonomics? Well, what we're doing is attaching brains, individual brains, collective brains, to more powerful systems that don't necessarily express the same human intent. And I'm very anxious to hear Brian later talking about from individuals or dyads to groups, because of course, emergent properties from groups don't express the same thing as the suit that goes into them. And so I see neuroergonomics and social neuroergonomics as absolutely critical. So many people conceive of the solutions to our existential problems pretty much solely in terms of the technology. I believe that's a vast mistake because it misserves the idea of the intentionality that human beings inject into all forms of system. And so I'm very glad to be able to be here today and talk about these particular issues. So autonomy, like love is all around you, autonomy now is pretty much all around you. It always has been. Human beings are relatively autonomous in and of themselves. And so we're used to interacting with to some degree with autonomous systems. It's just the type of autonomy now expressed is not human in nature. And it may very well be that we need this external linkage to go from the human brain to the human machine dyad and then the human machine group in order to understand these differing levels. So back to time. Time is my last point because time is the thing that's bearing upon me now. So there is just a general perception, indeed the perception of time, that time is a fairly linear, what I've called equipotential, immalleable flow of events in the world around you. It's what Isaac Newton conceived of as time, and it's the T of physics, the way in which the world is structured. And the T of physics, interestingly, has no concern with human experience. So a second that occurred 10 seconds ago is to a physicist the second that will occur in 10 seconds time. But if you are on the edge of the top of a roller coaster and the 10 seconds is the point at which you started the ride, and 10 seconds time you'll be coming over the top of the ride, behaviorally those are extremely different perceptual phenomena between the two. As you know, it happens in your own life. Time is not necessarily linear to you in its perception. However, the time base that human beings is in no way privileged. Human beings believe that there's a privilege and that therefore any automated system or autonomous system shares that privilege or that assumption. We often call it transparency. We often talk about how the machine should be transparent to us. And what we mean by that is that the machine should explain to us what it's doing. But of course, the machine is being built to do what we cannot do. We are not purely biomimetic in our principles in neuroergonomics. And I believe biomimetics is a two-edged sword. If we try to recreate human beings all the time, that's a very poor, expansive notion of design. But we're constantly looking at the brain to see the advantages that biomimetic principles might render. But the simple point is that machines will not possess the same time base as human beings, nor will they see the reason to, if they see reason in any sense. So I think as well as replacing ourselves in space, instead of just understanding where our relative position is in the spatial world, we have to do the same thing in the spatial world. Now, I believe, and I've written in a small piece that I'll be happy to circulate, that the solution then to existential problems are not purely technical and they're not purely social. They are socially technical or socio-technical, and they combine then a vastly important understanding of both the human brain and the machine capability in concert together. So I see that as we try to begin to resolve these various problems that are pushing our environment right now, we need very much to advance the curriculum, the spread, the dissemination, and the impact of social neuroergonomics to help search for that collaborative solution. I believe autonomy can help us do that, but I believe also autonomy poses an interesting threat. And like any tool, it can be used in different directions. So thank you very much for allowing me to speak today. Just a quick word about Raja. I still miss Raja. I had thought that our arguments, our discourse, our would continue for a much longer period than it did. So it's wonderful to see the brainchild of Dr. Parasurman elaborating so fecundly and so wonderfully around the world. And there is the thing called time telling me I should stop. Isn't it interesting? One of the regular things of the world. So thank you very much, Eva. I do appreciate it. And I'll be, of course, very happy to speak to some issues if questions are raised by the people who are listening today. Thank you again.
Thank you so much, Peter. I was hoping you will be giving us a philosophical angle on the entire topic, and as expected, you delivered. Thank you so much. It was very interesting, and I will say I miss Raja every day when I do, research on social neuroergonomics. I ask myself sometimes, what would he say if I said to him, anthropomorphism, this and that? Would he think it's a good idea? Would he do his, like this chuckling that he always did? Or would he be like, no, Eva, that makes no sense. Just move on to a different topic. So he is with us always. Thank you very much, Peter. And we move on to Lorna now.
Okay, so I'm going to get my screen shared. Can you see my presentation slide? Okay, wonderful. I'm going to start out by saying thank you for the invitation to be here today. I'm truly honored to be among this list of superstars in the field. My name is Lorna Quant. I'm an assistant professor at Gallaudet University in Washington, D.C. Gallaudet is well known for being the primary institution serving deaf and hard of hearing undergraduates, and you'll see that reflected in the work I share today. Somewhat similar to Emily, my background is really in action perception. So I've done a lot of work in the cognitive neuroscience of how we understand and perceive and make sense of other people's actions. And as you'll see in this talk today, my work has taken a turn to emerging technologies in a way that I never would have expected, but is allowing me to explore some really interesting questions in this field. So I'll be taking on challenge C today, probably not answering any of the questions in this challenge, but more like highlighting their importance. And I'll do that by talking to you all about embodied sign language learning in virtual reality, where I use EEG as an implicit measure of learning. So we'll start by talking about learning as a social process. So far today, we've talked about a lot of different types of social interactions, and I will make a case for learning as a particularly important type of social interaction. And then I'll explain a little bit of how that relates to the work that has been going on in my lab for the past few years, and how we can evaluate those types of social learning interactions. So we have new exciting tools, emerging technology that can allow us to learn in different ways. So thus far today, I think there's been a lot of discussion of humanoid robots or other types of physical technology that we can interact with. My work and my interest has really focused on something that's not as physical, but instead is virtual. So I'm very interested in social robots, but I don't have particular research experience with them. Instead, what we focus on in my lab is virtual learning in virtual environment spaces. So back to the learning. I think that the best learning is social. And I think that much research would support that statement, that learning when it occurs in a social situation, either with a teacher or with peers, is a richer and more likely to succeed form of learning than most other alternatives. You can read from a book, but you can also learn in a classroom from real people. So virtual reality, which I'll talk about VR today, but we could also talk about mixed reality or augmented reality. Virtual reality, when you put on a headset and you enter an immersive three-dimensional space, allows you to engage in a few different types of learning. Of particular interest for me is learning from a person in VR. What can that look like, and how do we know if it's working? What does it mean for that to work? So an important point of learning in a virtual space is, if it's social learning, who are we learning from, or who are we learning with? So imagine that you were doing a job training or trying to learn a new skill in virtual reality. You might be interacting with a sort of teacher or a guide, and they look a certain way in virtual reality. How does that matter? How do we figure out what they should look like or what impact that has? Up until a few years ago, I might expect that learning from a virtual human would look something like the upper left, where we have sort of a blocky, chunky, low-res person. Animation and the rendering have increased the capacity of building virtual humans to levels that we would have thought were impossible not long ago. So the most recent release that I'm aware of that really made my jaw drop is these meta-humans from Unreal on the lower right. And this is a tool that anyone can use to create virtual humans, and they can be placed into virtual spaces. So very soon we're going to be interacting, or we'll have the capability to interact with virtual humans who are not real, who look real. So what will that be like, and how will that impact what we can do in virtual spaces? Also, if we can design a teacher or design a character in VR, how should we design them? What should they look like? These questions I come at from a sort of social neuroscience perspective, but you could just as easily come from a number of different backgrounds. Animation, design, user experience. As we all know, this is truly interdisciplinary and requires input from all of these fields. So what makes a good virtual social interaction? If you're interacting with people in VR, how do we know if that's going the way that it should? We can turn to the same types of fields that we would ask about real life, non-virtual interactions: social neuroscience, social psychology, cognitive neuroscience, human dynamics. And I think that something that has stood out to me in looking at virtual interactions is we have to be cognizant of what is the goal of that interaction. So if I go get my Oculus Quest headset and put it on, there are a number of different social things that I can do in my virtual reality space. I might go virtually hang out with people to watch a concert, and those could be real people or they could be just avatars. So I might be looking for entertainment. There's also been a rise in like virtual co-working spaces. So if we're all home because of COVID, maybe Ava and I could put on our headsets and work in a virtual coffee shop together, and it would feel maybe like we were really together. Or you could look for social connection in VR, just that pure, feeling of connecting with a person. So there are many different types of interactions, but what about learning something from another person in VR? We could learn from a teacher, we could learn from someone who's training us to learn a new skill. Maybe we're in a virtual classroom with other students. But I think it's important to remember for any analysis of these new types of virtual interactions that different things matter depending on what the goal is for that interaction. So I'm particularly interested in how we teach a specific skill in virtual reality. For the past few years, my lab has been working on developing an American Sign Language teaching tool in VR, developing and testing that. And here I'll talk about American Sign Language because we're in the US, but this could be applied to any sign language from across the globe. what motivates the idea of taking on this research? Why would we want to? Why now? So I think that there's some evidence, and it seems clear to me as a person who has been learning ASL, that learning from a person is much more successful and better than learning ASL from books or videos. All sign languages are three-dimensional. They're, fully fledged languages that are expressed on the hand, body, and facial expressions. They require, fluid movements through time. You can look at books to learn ASL, but it's not going to be the same as learning from a person, whether that's virtually or in person. Like learning to dance, you would not want to learn to dance by reading a book. So we felt a desire to make it happen. Let's do this in VR. At the same time, we realized that the technology for making fluent avatars who can produce and communicate in sign language has advanced to the point that it's not too hard to make high quality fluent avatars who we make them using motion capture, but there are a few different ways. But we can make virtual humans who sign and it looks pretty good. And that was not true until recently. And finally, I'm interested in this question because it really capitalizes on the idea of embodied learning. So when we're learning to sign, whether in person or in a virtual space, how are the embodied learning mechanisms that we know are present in the human brain contributing to that process? So I'll show you what our system looks like. It is called Signing Avatars and Immersive Learning, or SAIL for short. And like I mentioned, we're combining here embodied learning, virtual reality, and these high quality motion capture signing avatars. So I can show you a quick run through of what this looks like. A user puts on a head mounted display, and here you see the immersive virtual space is being mirrored on an outside monitor. But for the user, it really feels like they're there and interacting with this character. So this is our teacher avatar, and she teaches basic American Sign Language to the user in 3 dimensions. So you can see they're having a somewhat social, somewhat interactive exchange in this virtual space. There's also room for improvement, but we won't go into that too much right now. But we've shown that this is possible, and we can create this sort of teaching environment where a teacher guides a user. But we wanted to put a lot of thought into how to make the teacher, because as you've already heard from the other talks today, and we know from the research, it matters. Does the teacher look like someone who you would want to learn from? Do they look real or too almost real and they fall into the uncanny valley? Are they too robotic? So we discussed, all sorts of different choices along various spectra. And we wanted to create a teacher avatar who would be producing clear signs, expressive in hands and face the way that we needed her to be, and who would also have the sort of more intangible characteristics of seeming warm and competent. So we've done some user ratings, large scale online user ratings, to show that people do generally find her to fit these characteristics. But this is a version from right before the pandemic, so still improving. But I wanted to point this out because we know that in an online virtual learning environment where you're interacting with a person, a lot of a person's experience is going to rely on how does your teacher avatar look, how do they move, and how do they communicate. And this is a good time for a caveat with this work. If you want to teach someone a new skill, such as learning American Sign Language, it is probably best to do that in person with face-to-face interactions with people who are fluent in the language. So we don't want to argue that what we're doing is better than real life, but rather that it can inhabit a in-between compared to those real life learning interactions in comparison to something like teaching yourself from a YouTube video. Of course, there are VR learning experiences that can't be replicated in real life, or are very, very hard to replicate. So there are, things where you can learn how to do mechanical and repairs on like the International Space Station because you're in virtual reality. But for us, we're just trying to replicate the good parts of a real in-person experience. So on to our challenge. We have an interaction with a virtual human, and we can put people into this experience and they can learn some new skills. They can learn some new vocabulary. How do we know if it's working? So I'm going to walk you through some thoughts about this in general, and also what it looks like for the project that I've described here. I think everyone who's watching this already has the idea that if we want to evaluate something like social learning, we can do that in part using behavioral measures. We can ask people for, how well they recall things, or give them a test, or, any number of sort of traditional learning outcomes. And we can combine that as well with neural responses and also psychophysiological responses. The goal of combining these two types of measures would be to provide a more complete picture about what responses are there during a social learning experience like this. So for something like teaching sign language, which is a physical, social, and embodied learning task, we're using our hands, bodies, and the physical space around us to complete the learning task. It is inherently physical. So for this particular instance, we're looking at this through the framework of motor resonance. So how much does the viewer embody the movements of the actor, and how does that change based on whether you are engaging with the teacher in a 3D immersive space compared to perhaps watching a video of the teacher? So looking both at the effect of interacting with the teacher and the immersive nature of that interaction, where you can feel the 3 dimensions around you. And this is motivated not just by the idea that motor resonance might be relevant, but a lot of research, which I'm sure my colleagues are familiar with, and hopefully the audience knows some of these ideas as well. We know that for certain types of learning, more sensory motor activity in the brain is related to better learning outcomes. So for instance, there's a study about learning physics, and when you have an embodied learning experience where you use your body, we see a mechanistic path for greater sensory motor activity leading to better learning outcomes. Another reason that we might look at neural responses to support our evaluation of learning is that neural measures can also reveal embodied processing on a pretty short time scale. So for instance, using EEG, you might be able to see changes that occur just from a brief amount of experience with a particular training or with a particular action. So those might be missed if we were to use only behavioral measures. So to break it down, if we want to ask whether someone is engaging in embodied learning in interacting with a social interaction with a virtual human, we could look at the sort of traditional aspects of learning. Did they retain the information? Do they know more than they did at the beginning? Can they remember what they learned? But we can also look at the more mechanistic embodied aspects by using a number of different neuroscience methods. So just for instance, we can look at sensory motor activity using fMRI or EEG, or we can use TMS to disrupt the system and see how that impacts learning. I'll show you what that looks like for this particular project. So we built the 3D learning environment, and what we want to ask is how that experience being in the virtual reality exchange with the avatar, how does that change our later our later processing of the content compared to other types of learning experiences? So this is work that should have happened during the pandemic, but could not. So I'll use the future tense because we'll be back at it as soon as we can. We'll be comparing the SAIL virtual reality group to a separate group of participants who see similar content, but not in immersive virtual reality, and a third control of a VR group who's learning a different language. And we propose that after training, we'll measure the EEG mu rhythm in response to the learned and unlearned ASL signs, a sort of paradigm that we've already shown what the EEG mu rhythm is doing when people do and do not understand ASL signs, if they're familiar with the content or not. But we will use that as a measure to look at the engagement of the sensory motor cortex. So this is one particular way that we can look at the mechanism that we are interested in. Specifically, we hypothesize that we'll see more sensory motor engagement and better learning outcomes from the SAIL VR condition due to the more three-dimensional and immersive nature of that social interaction. And so this comes to our challenge, which is combining the explicit and implicit measures to assess learning in VR with this virtual human. And, we could use any number of other implicit measures. So we might be looking at things like physiology and, we could add on a whole number of other ways of measuring this, but based on the theoretical framework that we're working within, for us, it's important to look at this mechanism of potential embodied learning. But taking a step back from that particular example, as I was reading the paper that sort of started this webinar, I was just reflecting on the fact that all social experiences, whether with a humanoid robot, a virtual human, or a real human, are multi-layered and contain things that we're conscious of and things that are underneath our conscious level of perception. So it seems intuitive and necessary that measuring those experiences just has to involve multi-dimensional approaches. And no specific measurement is going to give us all the information we want, but by combining a few, particularly those which relate to the theoretical framework within which we're working, we can get closer to understanding the human social phenomena that we're looking at, whether that's human machine, human virtual human, or any number of other combinations. Okay, with that, I'll say thank you to the NSF for our funding and my colleagues and students, and also put a plug for we're now hiring a postdoc. So someone let me know if you're interested or if you have any ideas. And that's it for me. Thank you so much, Eva.
Thank you so much, Lorna. What a great talk. I love your research. I would really love to hang out with you in a virtual coffee space soon.
I look forward
so
to it.
much. We are collecting questions. There are already questions in the chat. Moving on to Brian, really excited to hear your talk.
Thanks so much, everyone. Let me do the magic screen sharing here. Very good. All right. Perfect. Now I can see. Okay. This is a fantastic meeting and it's a new community to me. So thank you so much to the organizers for inviting me. I can always tell that it's a really interesting group because I change what I want to say about 8 times after listening to the previous talks. So thanks so much for this opportunity. I build robots not because I'm interested in technology, but because I'm interested in understanding human behavior. And I've spent much of the last 25 years building a pretty wide variety of socially interactive systems, most of which that engage with kids, just because that's where my developmental interests lie. But over the last few years, we've become more and more interested in how to take what we've learned with these social dyads and start to apply them into group settings. And we have been both pleasantly surprised and unfortunately shocked at how much things differ when we do make that leap into multi-party interactions. So I want to share today 4 very quick lessons of what we've picked up as we've tried to make this transition. And these are all lessons about people, not lessons about robots. So let me dive right in. The first lesson is that the social cues, even really basic social cues, differ completely when you're working with groups rather than with individuals. And the systems that we've built to recognize particular social states when we're working one-on-one crash and burn and are useless when we start dealing with groups. My favorite example of this comes from some work that Yolanda Light, who's now at KTH, did while she was a postdoc with me. And she was interested in how to study emotional understanding in children. So we had partnered with the Yale Center for Emotional Intelligence, who had this wonderful curricula designed to tell 3rd grade students how to deal with bullies. And the problem with the curriculum was that it involved role playing, and for the most part, the students didn't want to do it and the teachers didn't want to assign it because they were desperately worried that if they ever picked 2 students and then there was a problem between the 2 of them, that someone was going to get sued. But they were perfectly happy to have this be done with robots, and the kids engaged completely, and they wanted to help the one robot who was being bullied by the other robot. Now, what made this interesting in our setting today is that Yolanda did this both with single individuals interacting with this pair of robot and with groups of students interacting with the pair of robots. And I'm going to show you just a couple quick video clips that's going to tell the entire story for me. So here is one student interacting with the pair of robots. The robots are on the left and right sides of the video. And you can tell that she's completely engaged. She's looking back and forth between the 2 robots. She's interested in paying attention to what's going on. Whereas we came back a couple days later and she was completely bored that day and stared off into space and stared occasionally at the robots, but was not at all. It's obvious from her face that she's not engaged in what's going on. But when we did this with groups, the groups that were engaged often just stared straight at the robots or straight ahead. They did exactly what our disengaged single individual did. Whereas when they became disengaged, they started mostly interacting with each other, sometimes looking back and forth between the robots. There was also a lot more slapping involved when they were disengaged, but this was the kind of behavior that we saw. And when we trained machine learning systems, perception systems, to watch for these particular cues, and we trained it to recognize social engagement and social disengagement, in fact, the systems that we built were completely different. They didn't use the same low-level features. When we tried to use one trained on individuals to work with a group, it failed completely. That is, staring at the robot when you're all by yourself means that you're disengaged and you're spacing out in what's happening. But staring at the robot when you're in a group means that you're focused and you're actually paying attention. So even our basic understanding of what are social cues suddenly changes when we start dealing with this group setting. Okay. Second, when we look at what robots can do, we know that robots do trigger group level behavior effects, but sometimes they take just a little bit more to get at them. One of our favorite group level effects is conformity, and everyone knows Ash's classic experiments from the 50s and 60s, where we show you a line and we ask you which one of these others, A, B, or C, is the closest in length. And sure enough, if we ask you this by yourself, you'll perform at about 100%. But when we put a series of confederates before you who answer incorrectly, about a third of you will go along with that incorrect answer, even though you know it's absolutely right. Now, when we try to replicate this same effect with robots, it doesn't work. That is, if I put 4 robots and they all say which line matches and they all say A is the closest match, you'll look at them and say, those are dumb robots, that doesn't work. The right answer is C. Well, we're working here with a social grouping where not everyone is equal. And so when we take that into consideration and we start looking at a more ambiguous task, suddenly we'll see these group level effects emerge. This is some work from my current PhD student, Nicole Salomones. So Nicole took a more ambiguous task. She took a series of these very conceptual art pieces from a game called Dixit. And one player gives a single word to try to point to one of the cards and get all of the other players to select that same card. So we did this with robots, the same little keep-on robots that you saw before. And one of the robots said a word, lonely. And everyone, 3 robots and the human, all answered on a tablet what they thought was the correct answer. Now, no matter what the human said, we faked the rest of the voting. And we always responded with the top 2 choices, one of which was the human's response. In one condition, we told you explicitly what the votes were. 3 votes for one image with the bench, 1 vote for an image with the snow globe. And in the control condition, we told you the top 2, but didn't tell you what the vote was. Now, you knew if you were in that experimental condition, you had voted for the snow globe and we faked the robots' votes so that they all voted for the bench. And we then gave participants the option to change their answer. And in fact, when they were faced with that knowledge of the rest of the team, the rest of the robots in this case, voting against them, again, about a third of them switched their votes. That is, we see this group level behavior, this conformity effect, suddenly taking place where groups of robots, pieces of technology, are influencing the behavior of people. Taking the answer that they thought was right, that they gave initially, and getting them to change their response. Okay. So if robots can do that, if robots can create these group level social effects in groups of people, can we use that for some kind of good? But not only that, we know here that a group of robots is impacting one person. Can we get a single robot to influence the behavior of a human group? So let me now turn to my third point. That is, robots can influence not only the behavior of the group, but also individual behavior, that is human to human behavior within the social team. This is some work from Sarah Sebo, who was my PhD student at the time and is now at the University of Chicago. So here's what Sarah did. She brought in a group of people who didn't know each other, and they had to play this collaborative game together, 3 humans and 1 robot. And in the game, they're building little pieces of a railroad track. And at the end of each 2-minute round, they're told whether they individually have succeeded or failed, and whether the group as a whole has succeeded or failed. And the group only succeeds if the entire team succeeds. Everyone has to win in order for the group to win. Now, no one is, however, told whether anyone else individually has succeeded or failed. Now, we basically faked it again, and so we were able to rig the game so that we could control exactly when and where and to whom failures would occur. So that was kept constant throughout the experiment. The only thing that varied was what the robot did when there was a failure. So in our control condition, a robot said basically some relatively non-charged utterances. So we've completed 14 rounds in 18 minutes, blah, 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 blah. And in the experimental condition, the robot said something in an attempt to try to connect to the rest of the group. Awesome, I bet we can get a high score, just like I scored really well in my soccer game. In the control condition, we'd say things like, we didn't place the root accurately, one of the 32 pieces was out of place. And the experimental condition said, I sometimes do better with shapes than with numbers. Maybe that's true for you guys as well. So the only thing that differed here, not the number of failures, not who had failed, the only thing that changed is what the robot was saying. And sure enough, that was enough for us to see differences. So just to show you what it looked like, here's one of the experimental conditions. The guy on the left is going to be forced to fail at this, even though he doesn't realize he's being forced into failure.
It's okay.
Ah, that's too bad. Even though we may be afraid to make a mistake, it's okay. We're in this together.
He's very supportive.
So people liked engaging with this robot. They thought the game was kind of fun. But what we really wanted to see was, did the robot's utterances actually change the behavior of the group? Now, in this case, he admitted right away to his failure. But honestly, the game was really simple. And these very high-performing undergraduates at university, they wanted very much to show that they could succeed at what really looked like a children's game. And so many people, when they failed, they didn't admit their weakness. They didn't admit their failure. But more often than not, in the experimental condition, when they made a mistake, the person they looked to wasn't one of their human companions, it was to that nice supportive robot. And when the robot said something, they responded to it right away. Here's some examples of that. So make a mistake. Everyone who's being highlighted here has made a mistake. And as soon as they make a mistake, you know who they look at? The robot, the nice, friendly one in the group.
We're in this together.
Sure.
We're in this together.
Fist bump.
I made a mistake this round.
Damn it.
We're the winners.
That one was hard. I was proud of it.
Robot.
Like, you're not supposed to make the mistakes.
Now I have to pause that one for just a second because I want you to watch that last one again. Oops, let me pause it. Because the guy on the left, the guy who says to the robot, "Damn you, robot," he's actually the one who's made the mistake. The robot is covering for him in this little interaction. So let's watch that one more time.
I made a mistake
There
this
he
round.
is.
Damn it.
We're the winners.
That one was hard. I was proud of it.
Robot.
Like, you're not supposed to make the mistakes.
And sure enough, once we see people acclimate to this, we see them be more often to explain their own mistakes, to admit to what they've done. They're more often to act in some way to console a team member. And they're more often laughing with the rest of the team rather than feeling bad and introspective. All signs, good signs of trust in the team. So here, just the change in what the robot is saying is changing their behavior, not just directed to the robot, but to the other people within the group. Okay, let me come to my last point then. Understanding this difference as we move to groups is not just interesting, sort of facts about people, but it's also essential to us being able to build useful tools and useful technology. Those of you who know me know that I'm fascinated with trying to build systems to help kids with autism spectrum disorder. And we spent 15 years building a variety of different kinds of tools and finding out lots of interesting things about how we could try to leverage the fascination that many of these kids show with the technology devices that we have in order to produce something that's actually valuable to them. And we made a very big mistake for many years. And I say we, meaning the entire field, not just me, but I was certainly guilty of it without a doubt. That is, we were so focused on how these kids responded to the robot that we focused exclusively on that interaction, child to robot. And we looked for ways that we could improve that. We looked for ways we could leverage that. But in fact, we were sort of staring at the wrong thing. In fact, the successful things that we've been able to build with this have focused not on interactions between the child and the robot, but on triadic interactions between the child and the parent and the robot. And only when we start to introduce that triad do we actually start to see kids making significant improvements. So this was a study from a few years back where we put robots in homes for 30 days of autonomous social skills training. And this was an enormous undertaking. I think it took us 4 years to actually get all of this together. It was a collaboration with 4 other universities. And in the end, it's probably one of the largest deployments we've ever done. It's also the scariest thing I've ever done as a scientist, because the idea of putting this robot that is learning and changing and adapting into a home, all autonomous for 30 days, I couldn't imagine what was going to come out of it. But when we looked at what happened, this robot engaged the kids and one of their parents or guardians with these social skill games, the same thing that a therapist would have done if they had been able to visit the home for 30 minutes every day. And we played a set of games that are based around the same kinds of social skills that we were looking to train. And we did this in the worst possible environment that we could imagine, the bedrooms of teenagers. And for the most part, we would rather build robots that go out onto the surface of Mars than into the home, because Mars is much more predictable than anybody's individual home is. But all of that engineering, I think, would have gone completely to waste if we had focused just on the interaction between the child and the robot. Because what the robot did was not trying to enhance that relationship, but rather trying to focus on getting the child to interact more with the parent. So we did a lot all at once here that was different and new. We had this focus on triadic interactions. We were completely autonomous. We were adaptive and personalized. We were in the home. And we actually tried to do the most comprehensive evaluation that we've ever done with one of these studies. That is, we looked at multiple different dimensions of whether the children were learning something or not. We looked at whether they were getting better at the games that we presented, and sure enough, they were. We looked at the subjective reports from the parents and asked them, are they doing better between the beginning of the month and the end of the month? And they all said they were doing better. But most importantly, we brought in an outside set of clinicians, and we had them evaluate the children, such that if the children were going to show an improvement here, they would have to take what they had learned with the robot and the parent and transfer it to a different person in a different setting on a different task. And sure enough, 30 days with the robot was enough to do that. I think, though, the best summary of this comes not from us and not from our statistics, but from the parents themselves. So here's what one mother had to say, and I'll finish up in just a minute.
Sometimes the therapies they get a little exhausting, and he's not excited, and this one wasn't like that. He was ready to play at 7:30 in the morning. That we went to the playground one day, and I noticed immediately there was a group of children playing in the sand, and he walked up to them and said, "Hi, what are you doing?" And I don't think he would have done that a month ago.
This particular family, you'll notice their bookshelves are all empty. The parents have gotten a new job and were supposed to move in the middle of this month, and they decided to ship all of their other belongings away and finish out the month with the robot because they couldn't imagine leaving it behind. That's the kind of impact that you can have when you're focused on the group, not on the individual. Okay, so to wrap up, I think there's been some just initial steps towards dealing with these group level effects. But I think it's essential that we deal with them. And I think it is really a grand challenge, because it is questioning everything that we've done before and finding new ways to make those sort of one-on-one interactions scale out to the group is not just a simple matter of throwing more engineering at it. All right, since we are live streamed, I'll put up a set of references, just say this is where you can go and find more information. And if I had thought more carefully, I would have also mentioned some work that we've done with Joy Hirsch, looking at some actual brain differences when people make eye contact. But I'll have to leave that for another day. Thanks very much, everybody. And I'll turn it back to our hosts.
Thank you very much, Brian. I think you definitely, from my perspective, always have the nicest paradigms. You know, it's like, I wished my robots behaved so well as yours. And it was a very inspiring talk. Thank you so much. You definitely have already made a lot of progress in addressing some of the challenges that we raised earlier. So thank you very much.
Thank you.
Moving on to our last speaker, Antonia Hamilton.
Let me get my screen share set up. Let me share this and okay. Is my screen share visible with my slides?
Yes. We don't see it in presentation mode, but we see the slides.
Yes, it's now, but now it's in the wrong kind of presentation mode, isn't it?
Yeah,
That should be better. Yes. Okay, great. If everything's working, then I will start talking, because I have loads and loads of things that I want to talk about today. This is really going to be a very methods-focused talk. I want to go very, very rapidly over some of the types of approaches that we're using in my lab to get neuroimaging outside into the real world. And I'm not really going to talk about cognition very much at all, but I just want to say these are some of the things that the technologies can do, and also some of the methods challenges that we face in trying to use these new kinds of technologies. So I was trained in fMRI, the kind of classic cognitive experiment where you put a person in a scanner and they lie still and they watch little stimuli and we can see lots of brain activity, but that's very, very constrained. Often, you know, your only motor options are 2 response keys. You have to keep your head still and things. Now my lab is using FNIRS, functional neuroinfrared spectroscopy, which means that we can suddenly get outside all of these constraints of an MRI scanner and go out into the street, into the real world, into social interactions. And that suddenly opens up a whole lot of new challenges of what actually should we be studying? What kind of experimental design do we use when we're no longer constrained to, you know, simple events? And what kind of analyses and things do we use to look at that? So I'm going to start off with a very rapid introduction to FNIRS. I wasn't terribly sure if other people were going to talk about this already today, but just so that everyone is on board with the basic principles of this. FNIRS uses infrared light, and you have sources of infrared light. The light can go through skin, it can go through bone, it can get down to the surface of the cortex. The light that gets down to the cortex will be scattered. It's typically scattered along this banana-shaped path and gets picked up at a detector. The amount the light is scattered will depend on the absorption of the tissue just here in this bit of cortex, and that will depend on things like the amount of oxygenated and deoxygenated blood in that bit of the cortex. So if we send in different wavelengths of light, then there's different absorptions curves for the oxy and deoxyhemoglobin, so we can get nice measures of that. This is a measure from my primary visual cortex, and the black dark bit here is seeing lots of flashing lights, and the pale bit is when it's not seeing anything. So you see a nice clear response. It looks very, very similar to the fMRI signal because we're measuring the same stuff as you measure in an MRI scanner. You're measuring this change in blood flow in the cortex, and we typically get an increase in oxygenated blood and a decrease in deoxygenated blood when you turn on the visual stimulation. So the signals we're getting at look just like MRI. We can analyze them with many of the same principles that we use for MRI. We can relate it very closely to what we already know about brain function from MRI studies. But we've got a whole lot of different options in terms of the types of experiment, the types of participant that we work with. We don't just want to do FNIRS as a cheaper version of MRI. The kind of cases where this technology is really, really valuable are the cases where you want to do things that don't fit into an MRI scanner. So there's a lot of work with children and infants. I'm going to tell you about some work where we're doing outdoor tasks, walking around in Queen Square, walking around on the streets of London. It's very useful in low resource settings where you might not have access. I have some colleagues here at UCL who are doing studies of infant development in children in the Gambia, and they'll be putting their FNIRS on the back of pickups and driving out to villages and collecting brain imaging data. It's useful often with many, many patient groups who may be unable to go into an MRI scanner, people with cochlear implants, people with movement disorders or mental health conditions that mean that they can't go in a scanner. And then it's very, very interesting. And again, I'll tell you a bit about some data looking at social interactions where you've got two or more groups of people who can actually move about and engage with each other in a natural way. And we can still collect some brain imaging data in that context. So because I want to rush through some methods today, and I know I've only got a short time, I'll tell you about 3 different studies that kind of highlight some different things. First, a study of playing a card game, a bit like poker, where we look at lying and lie detection and a face-to-face interaction. Then a study of prospective memory, where we're going to get out of the lab and onto the street. And finally, a study where we're looking at actors performing Shakespeare on stage in the theatre, just because we want to try and push the technology to the absolute limit of what it can do and see if it's still possible to get meaningful data in that context. So our first study is looking at lying and lie detection. This has been done lots and lots of times in MRI with things like guilty knowledge tests. There's a nice one with a sort of dice game where you want to strategically lie to other people. But just asking someone in the scanner to press a button of have you seen this card before doesn't bear much relation to a more meaningful context where people lie. Often the context like police interviews or again games of poker, things that happen face to face. And one of the things that's challenging in those situations if someone wants to lie is to control what their face is doing, to control all these little non-verbal behaviors. So by using FNIRS, we can record from prefrontal cortex of 2 participants who are face-to-face, and they're playing a card game which allows them to lie or tell the truth. So on each round of the game, there'll be an informant and a guesser. So the informant will look at their card and can say either mine is higher or lower, and then the guesser has to decide if they're lying or telling the truth. So we've got a nice 2x2 factorial design for the trials where they're actually playing the game, and then some control trials where, for example, if the 2 cards are the same or they're the highest card or lowest card, we can force people to tell the truth or force them to lie. We had 35 pairs of participants do this task, and we're going to say, just is there prefrontal cortex activation when you're lying? Is there activation, for example, if you're telling the truth, but with the intent to deceive the other person? So is this about your intent to tell a lie, or is it about whether you're actually saying the word that's on the card or not? And I'll just show a couple of the contrasts here. If we look at just telling a lie, so the force, any trials with a lie compared to any trials with truth, we get some nice big activations in the prefrontal cortex. And also if you're telling the truth with the intention to deceive, again, we get some nice big activations across prefrontal cortex. We're analyzing the data here with a pretty classic trial-based design, just like you would do in an MRI study. But the nice thing is we can see this in both people at once, and we can see it in the face-to-face interaction. So just to summarize, what I've shown here is just how we can get data with FNIRS in this face-to-face context. We can see that lying in the face-to-face interaction engages some of these medial areas of prefrontal cortex. It's not just the dorsolateral areas that sometimes come up in the trad MRI studies. So I think the future question that leads on from this is, in this study, we had video footage just of a sort of side-on view of the participants to know when people were moving cards about and things, but we didn't have detailed face capture of their facial expressions and micro expressions. That's something that I think is going to be really, really important in this, and really important in future studies. We've got another study with a different, more controlled tasks where we do start to get at the facial expressions, but this idea of linking these little gestures, little social behaviors up to what's happening in the brain imaging data, I think is going to be something that's going to be very, very important for future studies that are doing hyperscanning analyses and using FNIRS to look at social interactions as well. So there's some other references to that there. The second of the studies I want to tell you about today is looking at prospective memory. So prospective memory is the idea of remembering something that you're going to do in the future. It's about intentions. And it's very, very easy to do. When I leave work, I think, oh, I've got to remember to buy milk on the way home. But 15 minutes later, I get off the train and walk straight past the corner shop. And it isn't until I open the front door, I go, darn, I forgot the milk. And so this is something where, we know that setting intentions, setting goals engages prefrontal cortex. And in a prospective memory task, you've got to maintain those goals over an extended period of time while there's various other distractions happening. And we wanted to contrast social and non-social prospective memory. As a social example might be Little Red Riding Hood remembering to stop at grandma's or remembering to do something that's related to another person, compared to remembering to do a non-social thing like buy the milk. And are there slightly different brain systems for those, or is there different prioritization? Again, so prospective memory has been studied in traditional MRI studies, but it's pretty hard to find a task that is meaningful. You can have things like you see numbers come up and you've got to press a key for the larger number, but if both numbers are even, then you do a different task. So you sort of have overlapping tasks. And typically there'll be kind of an ongoing task that happens every trial. And then sometimes you've got to detect that there's a rare task. But again, there's not much ecological validity to that MRI scanner situation. So what we were doing with Paul Burgess, who's really the expert on prefrontal cortex here, is setting up a study that takes place outside in Queen Square in London. Our participants are wearing a wearable FNIRS system that gives us 18 channels across prefrontal cortex, and they're walking around Queen Square, which our building is here in ICN. So we started all of our trials here, and we essentially have a circuit around the square that participants have to walk. And as they walk that circuit, they walk the circuit 5 times, and they have to do a different task each time they go around. The task would be things like count the number of buildings with the word Queen on. There's a lot because it's Queen Square, or count the number of buildings with steps up to the door, and this kind of thing. So they're having to focus quite a lot on their environment. And because this is outdoors, there's always stuff happening. There's cars going past, people in wheelchairs getting in and out, general obstacles of everyday life. They've also, in 2 blocks of the task, got this prospective memory task. So the social task was that we had a confederate who would stand at specific locations around the square. And when they see this particular confederate, they've got to come and fist bump her. So she starts off here, and then when she's been fist bumped here, she runs around and pops up again here, and then pops up here, so she can move from location to location without being seen to, obviously. And then the matched non-social task is to come and fist bump the parking meters, which Camden Council conveniently places all around Queen Square. And so again, there's parking meters here. And each time for these targets, you tended to have to cross the road and spot it kind of on the other side of the road, past a row of parked cars. So we're giving participants a really rich, complicated environment and a lot of different things that they've got to think about in this task. And we're monitoring their prefrontal cortex, and then we can do your classic kind of analysis where we say what brain areas are engaged when you're doing the prospective memory task compared to just walking around the square without having a task. And there's some stuff in prefrontal cortex. And then what's the difference between the social prospective memory and the non-social? And there's some stuff over here in the dorsolateral prefrontal cortex. We lost, unfortunately, the channels on the other side, so we can't really say whether this is bilateral or not. But we can find, some nice stuff here that's concordant with what we've known from previous MRI studies. The thing that was very exploratory here was a secondary analysis where we chucked out everything that we normally do and say, well, most cognitive tasks, you take a task-based approach. So we know we've imposed on our participants a particular structure of the task, and then we say, what's the brain activity pattern look like when you're doing that particular thing? But with this big, rich, complex data set, we said, well, let's also try a method devised by my colleague Paola Pinti, where we look for a brain-first approach. We say we've got this massive brain activity data, and just occasionally in that brain activity data, boom, there's something that lights up the whole of the brain. There's loads and loads of channels active. Something interesting is happening in that brain. And let's see if we can identify those function events. And then we go back through our video footage and say, well, what was actually the real world correlate of this functional event that lit up a big chunk of the brain? So for this, we can take the FNERS timeline, and there's an algorithm called AID that I'm not going to get into the detail of, but it basically identifies particular points in that FNERS timeline that count as functional events where something interesting has happened, something interesting has engaged lots of brain. Then we map those functional events and say, what was the participant doing at that time point? So for example, if we look at the functional events, we literally map them out over the space of Queen Square. This is again the map of Queen Square. And these stars are the places where our important events happened, these targets that you had to go toward. And then the little colored dots are telling you where the person was physically located in the square, when a functional event happened. And we can see that some of these are clustering as our participant, they're walking this way around the square as they're approaching some here, for example, they're approaching this, they'll have seen that target and be ready to cross the road toward it. Or here on this side, again, we've got a big cluster of points as they're approaching the target. And we can look again how this BA10, the more midline regions, have more functional events when you're in the prospective memory blocks compared to some of these ongoing blocks when you haven't got the tasks. So we can sort of completely turn the traditional approach to analysis on its head. And this slide is kind of just a taster because my colleagues Paul Burgess and James Crum are doing a whole lot more analysis on this data. But I think I just want to show you the potential for actually doing neuroimaging analysis a very different way around when you've got these sort of rich, complex real-world data sets. So just to summarize this study, we've shown that it is physically possible to collect data outside the lab in the real world. You can use a block design where you're giving people different tasks in different blocks, but we can also use this brain-first analysis using an AID algorithm to actually identify functional events and then say what world of activities drove some particular functional thing that might be happening. Then the final study I want to tell you about is an even more quirky and exploratory one, which we did primarily as a public engagement project and because we had the opportunity to work with a fabulous group of actors who performed Shakespeare. But it actually really led me to think quite deeply about what's the relationship between things like neuroscience and the theatre, because in a neuroscience lab, we have specific roles, we have scripts. You know, we know that this is the experimenter and this is the participant. And for every participant who comes in, a good experimenter will have a script that you go through as you do the consents and you explain what happens and you give the instructions and you check people's understanding at each stage. And again, the participant has an expected role that they will play, that they will sit still at particular moments and be fairly obedient and this kind of thing. And then again, we'll then impose particular stimuli, particular events on our participants. And we want this to be reproducible, to be able to do the same thing again and again. We see the same in some of the traditional social psychology experiments, these kind of things where, you know, you have a group of people who stand on a street corner in New York and everyone points upwards and you see how passers-by respond to that. That is in a way a piece of interactive theatre that you're creating for your unwitting participants. And working with professional actors was a marvelous experience because what they're trained to do is do things that are repeatable every single night on stage. They can stand up and create Hamlet. And it's also incredibly social and it creates this virtual world, almost like the virtual reality, but it has some deep emotional engagement, some deep imagination. So I think there's some really interesting things that when we're trying to kind of create real world neuroscience to actually work with actors and work with the kind of techniques that they found that work in the theatre. Now, what we were doing in this particular study is, again, we wanted to see if we can push FNERS to its limits and collect neuroimaging data from actors who are rehearsing Shakespeare. And the experimental condition we wanted to look at was to do with the sense of self and the idea that acting might change your sense of self when you go on stage every day and take on a particular role that somehow changes, or maybe you suppress yourself. And we know that hearing your own name engages the medial prefrontal cortex. That's seen in fMRI, it's seen in infants, it's a pretty reproducible study. We wanted to see if that would also be seen in our actors. So we had 6 professional actors who were rehearsing scenes from Midsummer Night's Dream, and they would be rehearsing scenes where they're working in pairs. We collected data from them over 19 different sessions, always with FNAs on 2 people. And so in each recording session, they have some control conditions where they might be walking or speaking, and then some acting sessions where they're either playing a scene with Cobweb or playing a scene with Titania. And throughout this whole session, the cognitive events we're looking at were name call events. So a speaker would literally shout out in my voice the name of one of the actors, Charlie! So Charlie obviously then feels a sense of self at that moment. His partner, Hepsi, who's acting with him, for her, it's the control condition because she's hearing a name, but it's not her name. And so then we can switch the names about and also have the names during both the acting blocks and during the control blocks. And we can then use a fairly traditional analysis to say, what are the brain systems that are responding when you hear your own name, but you're not acting? And that was giving us the right DLPFC. What's hearing your own name when you are acting? That was giving us the left DLPFC with a significant interaction between them. Unfortunately, we lost the medial channels, which were the ones we really wanted to get here, because by having people walking and freely moving about, this really is just pushing the limits of what you can get on this technology in terms of the amount of head motion and things like that. But again, I think this illustrates just a method that you can use to take quite an extended, fairly natural behavior from these actors and then impose some external events on and see how the brain is responding to having those external name call events imposed onto some other ongoing tasks. So that's just a different way round of kind of, I guess, trying to find an experimental design that might allow us to get brain activation changes when we're acting. Again, this is a novel data set. We're finding a whole bunch of different ways to analyze this also in relation to, we have motion capture data, heart rate data, breathing data, all of these other things from these actors. So the summary of this study is that, you know, we can impose events on a very complex natural sequence, and then that lets us kind of push this FNAS technology to the limits of what it can do. And so I think I'm probably out of time and want to allow some time for questions. And I will finish there and thank all the people in my lab who worked on this. Thank you.
Thank you so much, Antonia, for this very inspiring talk. As somebody who has tried to use FNIRS in the lab, I can't tell you how much I am impressed by how many different complex application scenarios you have successfully applied this to. And it's certainly a technique that would benefit human-robot interaction in social neuroergonomics tremendously. So thank you very much for sharing your research with us.
We have some fabulous colleagues in engineering. That's the thing that's essential for making this work.
That's how it works. Thank you so much. So this concludes our keynote presentations. Thank you again, everybody who presented here. We were truly amazed that you immediately said yes to our invitations. This was really a fabulous group of people, and I think it really introduced the field of social neuroergonomics very well and gave everybody a lot to think about. We are now ready to move on to the Q&A session, and I hand it over to, I believe, Louis or Jesse, who will share questions from GatherTown with us. I hope. No. Oh, so we have it in the chat. All right. So I will just read it out from the chat then, I believe. So one question is to everyone: what is the relevance of the social variable in the study of prospective memory compared to studying it at an ecological context? Maybe we pause there because this question has 3 parts.
So you're asking about our Queen Square study, I think, and we want to, yeah, I can say it's for me. So the social variable was really because we wanted to be able to see, was there any difference between a social and a non-social prospective memory, or are they really engaging exactly the same thing? Your second question is, can brain connectivity be derived from FNERS? Yes, FNERS is excellent for connectivity, and because it has a much higher temporal resolution than MRI, you can often get more out of it in terms of connectivity data. There's a lot of work finding clever ways to do connectivity. And the final part, when engaged in event-based prospective memory in the maintenance phase, seems to recruit dorsal frontal parietal, and the retrieval recruits something else. I believe you. I am not the prospective memory expert. Paul Burgess is an incredible expert on prospective memory. For the detailed questions on that, talk to him. We're working to get this data published and get it actually out there. So he would be the one to talk to for the detailed cognitive interpretations of the task.
Thank you. Ready for the next question?
There were a couple of questions I saw way back when, but in the chat, but I've lost them now. I think there was one that came.
I believe they have been collected and will be shared with us eventually.
Okay.
That's my understanding. There's another question for you, Antonia.
Yes, Frederick asks, do you experience any issues of noise and interference when using motion capture and FNERS? No, we haven't. I mean, we've used a variety of different motion capture systems, but in particular, we haven't used an infrared mocap system. That could potentially cause interference. And I know some infrared eye trackers cause interference with FNERS depending on the frequencies you're using. For things like the acting study, we were using, it's called Neuron Mocap, and it's an IMU-based system, and that works pretty robustly. It's all wireless, it's quite cheap, and it all works at the same time as the FNERS. And Polyhemus as well, we've used a lot, and that works very nicely.
Thank you. Emily, there's a question for you on the TPJ, I believe.
Yes, I saw that question from Ali about, just to read it if people haven't heard it, but some argue no specialization for social behavior, but general complex behavior, whereas my findings seem to suggest both. So we kind of get this parcellation across parts of the cortex that are involved in social perception and interaction. And that's exactly right, Ali. I think it's categorically the case. We can't lump all these brain regions together and say that there's just kind of specifically social processing or not. It's not my work's kind of overarching goal to parcellate the social brain of the action observation network in super fine detail to say this is what's happening with these regions kind of in a general framework, but we do in individual studies start to take those apart. And you're absolutely right. What we find in our work in general is that TPJ is pretty, TPJ, strongly attuned to socialness, whereas socialness is a far more flexible construct, especially across premotor and parietal regions. But great question. Thanks.
Thank you. Then there are two questions for you, Lorna. Maybe you can summarize them first, if at all possible, and then answer them.
Sure. Okay, one person says, how about the potential of VR for training complex multi-level social skills, like leadership development, where you have situation-based role playing? So yes, I think people are working on that, and there may be some games or experiences that can be downloaded commercially that approach that, but I know in more like in the research space, people are working on using VR for that kind of like role-playing situation that you described, training people for different types of social interactions. I've also learned about interesting uses of VR for in like therapeutic purposes. So you can use virtual reality to expose people to things that they have phobias of in a, you know, sort of controlled and appropriately paced way. So there's a lot of work using VR to control and test how people respond to different types of social interactions. I'm not sure how much of that is out of the lab yet or not, but it's coming. And if you're curious, everyone should go buy themselves the more widely available VR headsets and explore for themselves, because there's a lot happening there.
Can I come in a little bit on that? Because we did quite a lot of social VR a few years ago and have almost moved away from some of it because I've been very frustrated by the technology, the limitations of the technology. I found it very good in highly scripted situations where you can set out a script that the participant says something, the virtual character says something, the participant responds in a consistent way. But if you do a real world social training, you're using the dynamic of the trainers to respond fluently and flexibly to what your participant is doing. And I've yet to see any virtual characters who can do anything remotely like that. And I think it's going to be a long way off before they can show that kind of very flexible social engagement, because really you're wanting a character that has all of the cognitive capacities of a human to understand the language, to understand the non-verbals, to create a sensible reply, and to do that online in real time and things. And so I think that there are some situations where we can structure it such that we get an illusion that it works. But do disagree with me, Lorna, because you may be much more up to date with things. But I'm actually pretty skeptical that it's going to really work for quite a long time.
Yeah, I think that you make a great point that VR can work sort of well for a very constrained purpose. So if you have a very specific type of interaction that you want to give people, it's possible to make something that feels good and approaches maybe succeeding in that very specific goal. But like the question asked about complex multi-level social skills, if you're training people to be a good leader, how many different skills does that require? Thousands. Things that we don't even understand. Even if you're a good leader, you can't put that into words. So I think, like Antonia says, we're not close to just dropping someone in VR for leadership training and they come out better at this sort of broad range of social skills. That would be a big ask. I think we are closer to a tightly scripted, constrained, small world of interaction or exchange being successful in a virtual world. But yeah,
I just want to say really quickly that some of Stacey Marcella's work is looking at kind of VR for leadership training, and there's some really interesting, again, it's not this whole scale panacea for how you can do that, but that's just a person's work that question asker might be interested in looking at.
Oh, maybe you can put their name in the chat, or I don't know if someone can't see that, but yeah, that's a great tip.
Cool. There's another. Sorry.
Oh, I was going to say there was more. There was more to one of those questions. Let's see. How about virtual reality interaction for neurorehabilitation? I believe people are doing this sort of like you can do mirror therapy in VR. You can do gait retraining in VR. I don't have a lot of specific knowledge about how successful those attempts are, but I know people are looking at leveraging the virtual immersive nature to, retrain the brain for functionality. Does anyone have any more concrete information about how those attempts are going? I don't.
I do remember seeing some videos of a really fabulous program where they were doing a sort of motor rehab, and they were training people to control a dolphin in VR. And it was really engaging and had again a lot of freedom of movement, so you could move your dolphin around in different ways, and that seemed to be very effective at engaging their participants to do these otherwise rather boring and repetitive exercises and things, and you could sort of impose different dynamics on the system. So I think for the motor side, there probably are things that work quite nicely.
We have a very large center at my university for post-traumatic stress disorder improvement through VR exposure. And interestingly enough, the one of the more impactful elements is the olfactory element. Obviously, these are military people, and there are certain olfactory stimuli that tend to trigger off these events, amongst which is diesel and oil. So certainly they're used for that. I have to say, as a point of history, that I had the first ever commercially bought VR headphones in the world long time ago. They were bought from Jared Lanier, and I know that they were the first ones because they had number 3 on the side. Number 2 didn't work, and number 1 didn't work. Number 2 was the one they always did for demos, so we got number 3. Sadly, I don't have them anymore, but it was fun.
Thanks for sharing that. We have, Lorna, have we answered all of the VR questions for now?
I think
How
so.
close are we to making this work practically?
It depends what your outcomes are. What's your goal? Full leadership training, I think we agree that's not close, but you know, perhaps there's room for less so of training and more so like exposure to social situations. So for people who perhaps have a disorder or have a phobia or have something that makes real world experiences too uncontrollable or too dangerous to be in. I know there's some work using VR for looking at the effects of environment in drug craving. So things like that, where you want to expose people to a very tightly controlled environment, those are perhaps more promising than the larger scale, complex, multi-layered interactions that we're asking about. And I think a common theme in my understanding of VR social interactions is, like Antonia said, it's really hard to close the loop. So if you want to observe something in VR, that might be more straightforward. If you want to produce some behaviors in VR, that can be straightforward. If you want to have contingent responses from a virtual human that depend upon your own behaviors, that's not easy. It's not to say it's impossible, and certain things have become much better in just the past year, like hand tracking, which is of interest to me for my work. Hand tracking built in on the Oculus Quest 2 is really, really good now compared to what it was like 2 years ago. And that allows for more types of interactions. So it's changing, but closing the loop is still the big challenge, I think.
I can give a practical example of that also. I work on a project looking at job skills training for adults with autism. And my collaborator, Nilanjan Sarkar at Vanderbilt, uses VR systems to train interview skills for adults with ASD. So it's a constrained topic. It's a relatively structured interaction, but one where there is a fairly large amount of contingency upon how things go in that interview. And they're going to relatively large-scale public trials this year. So they have some relatively mature technology, but it is within this constrained, setting.
Mm-hmm. Yeah.
Do you have any knowledge about how the participants with ASD reacted to the headset? Because sometimes, with EEG and fMRI, that can be challenging with that particular population.
It depends on the individual. You get individuals who have a lot of sensory issues and they don't respond very well. But the population they're looking at are adults with ASD who are high functioning enough to be looking for jobs and to have a potential for employment. So it's a subset of the broader population already.
Okay, thank you. There's another question to everyone. First feedback that the talks were incredibly informative. And then the question is how focusing or researching robots and social agents can inform us about collaborative scenarios in human factors, for example, search and rescue missions.
I think there's a lot of interest and work in this area, at least in Australia. My understanding of the defense departments here, like this particular type in human factors, especially human robot collaboration in high risk scenarios, whether it's search and rescue, space exploration, underwater exploration. This is where robots can really come into their own. Maybe not so much the particular types of social robots that we might be thinking of. It can be ones that are maybe not socially engineered, but can adapt to these dangerous environments. I would say, though, that I think there's a really big space for those of us interested in social perception, social interaction, social cognition to make contributions to these collaborative human robot teams. And I know that at least in the space around here, that work is really starting to take off. And I'm guessing in America, across Europe, there's also lots of interest from the military in this.
Right. I will say from my personal experience, when I first went to, and I go to HFES, so Human Factors and Ergonomics Society conference every year. And when I first talked about social robots there, that was, I think, now 8 years ago. It seemed like a pretty new field in human factors. The social seemed to make some people initially uncomfortable, but over the years I've kind of and this is absolutely anecdotal, but people are really warming up to the idea of both robots and social psychology, social cognition in the field of human factors. And so I have seen way more positive responses and also way more publications and talks about this topic recently.
Yeah, the person who I associate most with search and rescue robots is Robin Murphy. I think she's at Texas A&M now. But I think the collapse at Surfside recently here in Florida is another example where they attempted to use some robotic collaboration, but unfortunately, I don't think it was successful in this particular occasion. But can indeed, as someone said, those robots can continue to work even when nominally the site is too dangerous for humans to actually be physically there.
Yeah. There's quite a bit of work out there. You just have to find the right community. So it's relatively sparse at HFES and most of the human factors conferences. But if you look at HRI or Roman or Kai, some of the more technology focused areas, there have been good consistent papers in this domain for 15 years or so.
Thank you. There's a question for Brian. Did you work on more applied contexts like human operators, robot teaming, cobot issues? Thanks for your great talk.
Yeah, absolutely. There's, in addition to looking at these really high risk scenarios, the last 5 years we've seen a lot of interest in sort of the more mundane side-by-side manufacturing jobs or household tasks where you've got robots working, as cobots, as collaborative systems with a person. And we right now do a lot of work with tool use, actually, and coordinated tool use. So how do you get a robot to work efficiently in a manufacturing type setting, back and forth with a person, where the robot needs to, number one, estimate that person's skills and abilities, and to plan in a way such that it's being a useful companion. And that's a very different technical task than you would have for most standard robot planning tasks. So for example, if I'm building a birdhouse with one of my students, I'm going to do things that are not part of actually just strictly building a birdhouse. I might deliver a tool to them, or I might hold something steady for them. And when you look at normal planning systems, these things don't come up with those solutions at all. So there's a whole new field of collaborative planning that's spawned out of this area. Yes, we have some work in there. There's a lot of other people. I would point to Brad Hayes, who's at the University of Colorado, Julie Shaw, who's at MIT, and there's many other people involved. Maya Chakmak's another good one.
Thank you. It seems like we are out of questions from GatherTown, so I may place one selfish question here to all the keynote speakers. So listening to, or like seeing the challenges, the 5 challenges that we have formulated within the field of social neuroergonomics, do you feel like they address the challenges quite well? Do you feel like some are maybe already resolved or close to being resolved? And is there maybe a challenge that we haven't addressed that you would like to be among those? Take this as a compliment for my question.
I think that the work that was presented across all the speakers today soundly answers the had these been addressed. I don't think any of them have been addressed. Yes, with progress bars, we might see farther progress with some than others, but like definitely not. I think they're all very active and they're very well put, well articulated. So I can't improve upon them, but perhaps others can.
So I think it would be helpful, Eva, if you matrix the 5 challenges that you've indicated with the National Academy of Engineering hierarchy of challenges, because I think several of the things that we talked about today were quite often methodological, and I think they're methodological expansions as much as anything else. People are asking us to go out into the real world, quite rightfully so, and I've always found it a fairly strong criticism of experimental psychology that the small world of the laboratory really is just, I think, as Brian put it, exploded when you carry it into the real world. And I think the methodologies that we have, as was said earlier by Antonia, we're now starting to be able to carry them into the world, and the excuse of their complexity is no longer sustainable. But again, I think the methodologies must be combined with the domain element. So I would ask you to look at that and see how we can basically matrix the 2, content and approach.
That's a very good point. Thank you. I wrote it down. Thank you.
So I would add one other thing. I think that there are points at which we are coming to realize that while we see interaction with technology that looks like interaction with people, we know at some levels there are differences, and whether that is at the micro behavior level or whether that's at the neural level. And I don't think we have a good structure in place to try to characterize and understand those differences. We see many effects, experimental effects in the lab, where you see someone's behavior and it goes one direction, and you ask them about it later and they tell you a complete bald-faced lie about how they would have, they thought the absolute opposite thing. And when they're allowed to reflect on it, then things have suddenly changed. And I'm sure we have some revisionist history going on as part of this. But I think now we're actually starting to see some of these differences, not just at the behavioral level, but as we go further down into the neural substrate. So how do you deal with and characterize these differences when they show up? What does it mean that I process gaze from a robot in some ways like a person and in some ways not? How do I capture what that difference is, and what does it really mean? So comparing between those levels, I think, is the challenge.
I think that's an important point, and I don't usually bring up papers or experiments, but one thing we've used in our lab is use choice. So we have the people say what they're going to do, and then we put them to the test and look at which they actually choose, the human companion or the robot. And as you rightly point out, but the general point that you're bringing up, which I think is even more explosive, is the idea that people lie. I mean, with the pandemic, the number of students I now have who are doing survey instruments, and I ask them if they think people lie, and they say, yes, yeah, we do believe people lie. And so I ask them if they think they're lying to them on the survey, and they have no real answer because they just then show me data and data and data. So I think that is a very important issue, what people say they will do versus what they actually do. And yeah, I think we need better sort of observational techniques in order to establish that.
And I think this goes, at every level down. It's easy for us to talk about it at the behavioral level, but as we get slower, as we get lower and lower, we've said for years how people follow robot gaze, and if the robot looks up and to the left, everybody's suddenly staring up at the ceiling. But in fact, when you look at more fine-tuned metrics, it doesn't actually work exactly the same. If you look at counterpredictive cueing type paradigms where you train people that a face looking in this direction means there's going to be a target in the opposite direction, they can do that with human faces and not with robot faces. So there's a number of these differences that you just keep going lower. And as we get to imaging studies, we're starting to see those differences come out as well. Right. What do they mean? How do we characterize that?
I agree. Yes. I mean, somebody who has done gaze cueing research for quite some time now. I mean, you can put eyes on a glove, eyes on an apple, and you get the bottom up a gaze following mechanism. So it's really, and then you do get some top down modulation of that even with robots. And what works really well is instruction manipulation. So these top-down beliefs are clearly there. But what I also find really interesting is to see how they change over time, because I mean, you don't know anything about those robots. So what else would, I mean, it's clear that in the short run, this is what will happen. But then how do those top-down beliefs interact with actual behavior that the robot shows, and what, gets the stronger weight as time passes? I mean, I have my own thoughts about this, but it is really important to empirically investigate that, how this interaction between actual behavior and belief about the robot's behavior, how that plays out over time.
So it seems like we're going to have to rerun social psychology and redefine what we actually mean as social, right?
Absolutely. We like challenges. This is what this is all about.
I will leave that up to you guys, I think.
Well, I think I don't want to cut anybody off, but I feel like we have covered this topic from all sorts of angles. I'm really inspired. This worked out better than I thought, and I already had high expectations. I had a lot of associations. I can see my research overlap with all of you, and this was extremely informative for me. I would like to point out that some of us might move over to GatherTown and hang out. If you feel like it, you can join, but I also understand it was a long webinar. So if you don't feel like it, that's also fine, but let's keep the conversation going. And thank you very much for these inspiring talks.
Thank you. I can't join you in the Harbor Town, or what is it? Freedom Town.
GatherTown.
Other town, yeah, GatherTown, because of local constraints. But thank you very much. I had not only a great time, I really enjoyed listening to the other speakers. It was a great meeting. Thank you.
Thank you. Bye, everyone.
Thank you, Eva. Bye.
Bye.
Bye now.